Hi folks, the following video is going to talk about substitution reactions, elimination reactions, and oxidation reactions involving alcohols. Before getting into alcohol substitution reactions, I want to consider the OH group as a leaving group. That OH group of the alcohol is a really bad leaving group. So let's consider a potential reaction of an alcohol with a bromide anion. And we'll consider, can this bromide displace the OH group in a substitution reaction to form a carbon-bromine bond and hydroxide anion? To decide which side of this reaction equation is favored, you would want to compare the anionic species, bromide on the left to hydroxide on the right. We can decide how stable these anions are by looking at the pKa's of their conjugate acids, and as you can see, HBr is a much stronger acid than water, meaning that bromide, its conjugate base, is more stable. The equilibrium of this hypothetical reaction would favor the reactants, which is the side with the more stable base. So essentially, you could not treat an alcohol with bromide and get a substitution reaction to occur directly. In this video, I'm going to show you some methods you can use to convert the alcohol into a compound with a better leaving group that can undergo a substitution reaction. The first method I'll talk about is turning the alcohol into what's known as an alkyl sulfonate. A second method is activating the alcohol with a Bronsted-Lowry acid. And a third method is activating the alcohol with a Lewis acid. The idea in all of these different classes of reactions is that the alcohol itself has an OH group that's a bad leaving group, and you need to convert it into a better leaving group to get a reaction to occur. The first method I'll talk about is converting the alcohol into an alkyl sulfonate. This is a way of activating the alcohol to make that OH group more reactive and get reactions to occur. This is necessary because the OH group is a bad leaving group by itself, but once the molecule has been converted into an alkyl sulfonate, the sulfonate part of it is a good leaving group. So sulfonate refers to the functional group where you have your alkyl group connected to an oxygen, connected to a sulfur with two double bonds to oxygens, and an R group, some type of carbon group. What's known as a mesylate is a type of sulfonate with a methyl group attached to sulfur. This can be abbreviated as MS. A group called a tosylate has an aromatic ring with a methyl group on it attached to sulfur. This can be abbreviated TS. And a type of sulfonate known as a triflate has a CF3 group attached to sulfur. This can be abbreviated as TF. So these are three common types of alkyl sulfonates. Looking at these three sulfonates, the triflate is the best leaving group, and the mesylate is still a good leaving group, but it is not quite as good as the triflate or the tosylate. We can think about good leaving groups as being weak bases. So we could look at the conjugate acid of the mesylate, tosylate, and triflate. The pKa's of these are -2, -3, and -14, really much lower for triflate due to induction from the CF3 group. So the reason the triflate is the best leaving group is because it is the conjugate base of the strongest acid, meaning that it's the weakest base. A method for making a sulfonate from an alcohol is treating that alcohol with a sulfonyl chloride, where you have an S doubly bound to an oxygen, another oxygen, having an R group, and a chlorine attached to sulfur. You treat this chloride with the alcohol in the presence of pyridine, a base, and you remove the hydrogen from the oxygen and replace it with an SO2R group. If your alcohol is present on a chiral center, that chiral center is maintained. And actually, this oxygen of the alcohol is this oxygen of the alkyl sulfonate. Often people abbreviate the sulfonyl chloride by writing just TSCl, which is a tosyl chloride, this particular molecule. You still need to indicate the presence of pyridine, but this is a shorthand way of writing out these reagents, and people also shorthand the sulfonate as OTS commonly. We can look at the mechanism for formation of this sulfonate from the alcohol. In the first step of the mechanism, the oxygen is going to act as the nucleophile, and it's going to attack the sulfur, which will behave as an electrophile. I'll draw two curved arrows for this nucleophilic attack at sulfur, from an oxygen lone pair to sulfur, and breaking a sulfur-oxygen pi bond and bringing those electrons up to oxygen. This nucleophilic attack forms a new oxygen-sulfur bond. Oxygen has 3 bonds and a positive charge. Sulfur has a double bond to one oxygen, a single bond to an oxygen with a negative charge, and at this point it still has its R group and its chlorine. The next step of the mechanism will be a loss of leaving group from sulfur. I'm going to bring down an anionic oxygen lone pair to form a pi bond at the same time that I break the sulfur-chlorine bond and bring the electrons to chlorine. This is showing the pi bond reforming and chloride being lost. In this step, the oxygen that was originally the alcohol is still cationic. Sulfur is neutral, and both of sulfur's other oxygens are neutral as well. To deprotonate the cationic oxygen to get to a neutral product, I need to bring in a base. Here I've added pyridine as one of my reactants, and that's a good base. I would use the nitrogen's lone pair to deprotonate the oxygen's bond to hydrogen. And this proton transfer gets to the neutral alkyl sulfonate product. Notice that no chemistry has taken place at this carbon, this chiral center, so therefore the configuration is maintained. Nothing has happened at that particular carbon. Alkyl sulfonates are useful for synthesis because they follow the same substitution and elimination reaction rules that we saw for alkyl halides. For example, let's consider we're treating a secondary alkyl sulfonate with a nucleophile such as SH-. This is a strong nucleophile, weak base. Based on rules for alkyl halides, we would expect an SN2 reaction to occur, where the nucleophile would attack the electrophilic carbon and break the bond to the leaving group in the same step. The only difference here is that it is a sulfonate as a leaving group instead of a halide. The substitution reaction would proceed with an inversion of stereochemistry. And alkyl sulfonates can also undergo elimination reactions. In this example, I have an alkyl sulfonate, and I'm treating it with a small and strong base and a weak nucleophile. These are conditions for E2. Because this is a small base, I need to compare the beta positions, and I will preferentially react with the more substituted beta carbon containing a hydrogen. I could draw my 3 curved arrows of the E2 step. So here the alkyl sulfonate is undergoing an elimination reaction to form a trisubstituted alkene. Starting from an alcohol, the alcohol can be converted into an alkyl sulfonate before a substitution or elimination reaction, because remember the OH group itself is a really bad leaving group. So in this first example, I have a molecule with 2 chiral centers, one of which is a carbon attached to an OH group. The step 1 here, treatment with TSCl, tosyl chloride in the presence of pyridine, is going to convert the OH group into a tosylate group, OTS. This is a type of alkyl sulfonate. Notice that neither chiral center has had any change in its stereochemistry. Upon treatment of this alkyl sulfonate with NaBr, I have a substitution reaction involving the bromide nucleophile to displace the OTS group and replace it with a bromine. Alcohols can also be converted into alkyl sulfonates prior to elimination reactions. In the first step of this reaction, treatment of this alcohol with TSCl in the presence of pyridine converts the alcohol group into an alkyl sulfonate. This sulfonate is now a good leaving group, and it's being treated with a strong base and a strong nucleophile. Because this is a secondary alkyl sulfonate, you would expect elimination to be the major product, so this would form a cyclic alkene. So overall, the alkyl sulfonate is a convenient way of making an alcohol into a better leaving group so that you can perform reactions such as substitutions or eliminations that we've seen previously. A second method for activating alcohols to make them more reactive is to treat the alcohol with a Bronsted-Lowry acid. Here as well, the idea is that the alcohol itself is a really bad leaving group, but when it's been converted into a cationic oxygen, it's a good leaving group. What the general reaction scheme would look like is you're treating the alcohol with an acid to form its conjugate acid with a cationic oxygen. This cationic oxygen is now a good leaving group, so it could be displaced by a nucleophile in a substitution reaction, or your protonated alcohol could react with a base in an elimination reaction to form an alkene. The mechanism of these substitution or elimination reactions depends on the substitution of the alcohol. I'll begin by talking about primary alcohols. A substitution reaction for a primary alcohol would convert it into a primary alkyl halide. One example of this is treatment of an alcohol with HBr. In the product, you have a new alkyl bromide, and water has been formed. The first step of the mechanism is a proton transfer. The oxygen is going to act as the base to deprotonate HBr. I show the two curved arrows of that proton transfer step. That proton transfer would generate the cationic conjugate acid of the alcohol. That cationic oxygen is now a good leaving group, and bromide anion was formed in the first step. You can have a nucleophilic attack, where the carbon attached to the leaving group is going to be the electrophile. I would draw the nucleophilic attack and loss of the water leaving group in the same step. This would form the new carbon-bromine bond and generate water as the byproduct. You can also have elimination reactions for primary alcohols, and these will form alkenes. For example, let's consider this 3-carbon alcohol. The conditions for elimination are treating it with concentrated sulfuric acid. Assume there's a little bit of water present and you need heat. Heat is going to promote elimination reactions to form alkenes, often because the alkenes have low boiling points, so you can get them to distill away from the starting materials as the reaction proceeds. This reaction as well is going to begin with a proton transfer. In this case, assume that the concentrated sulfuric acid reacted with water to form H3O+. I'll use the alcohol oxygen as the base to deprotonate hydronium. This would generate the conjugate acid of the alcohol, where the cationic oxygen is now a good leaving group. Starting from a primary alcohol, the next step of the mechanism will be an E2 step. Because I'm under acidic conditions, water is the best base that's available, and I need to deprotonate a beta position. I'd use water to deprotonate that carbon-hydrogen bond, take the electrons from the CH bond to form a pi bond, and kick out the leaving group in the same step. This E2 step kicks out water as the byproduct, our good leaving group, and it formed the alkene product. In both of these cases, the acidic conditions are getting to the conjugate acid of the alcohol, where the water molecule is now a good leaving group, and you can have SN2 or E2 reactions occur. Substitution and elimination reactions can also occur for secondary or tertiary alcohols activated by Bronsted-Lowry acids. The first step of the mechanism, protonating the alcohol, will be the same, but the next steps of the mechanism will differ. Looking at substitution first, secondary or tertiary alcohols can be converted into alkyl halides by treatment of the alcohol with HBr. In this substitution reaction, the OH group is converted into water, and bromide is acting as the nucleophile. The first step of the mechanism is going to be protonation of the alcohol again. I'll use an oxygen lone pair as the base to deprotonate HBr. This forms the conjugate acid of the alcohol. And this protonated oxygen with the two hydrogens is water, a good leaving group. Because the alpha position is bulkier for secondary and tertiary alcohols, a substitution reaction by an SN2 mechanism won't occur, and instead a loss of leaving group will happen. I would break the carbon-oxygen bond and bring the electrons to oxygen. This step forms water and a carbocation, in this case a secondary one. This carbocation is a great electrophile, and it can react with the bromide anion that was generated in the first step, the proton transfer. I would have a nucleophilic attack. This generates the new carbon-bromine bond in the substitution product. So compared to the reaction for a primary alcohol, the first step is the same, but instead of an SN2 reaction, you have a two-step where you first form a carbocation and then have the nucleophilic attack, more like an SN1 mechanism. An elimination reaction for a secondary or tertiary alcohol would convert it into an alkene. Here as well, the reaction conditions are concentrated sulfuric acid, water, and heat. Sometimes the water may not be written, and you just have to assume that there's a little bit present, since it's formed as a leaving group in this reaction. The first step of the mechanism here as well is generating a good leaving group. To do that, I need to protonate the oxygen. This would form the conjugate acid, where the H2O molecule is now a good leaving group. For a secondary or a tertiary alcohol starting out, a loss of leaving group will occur, breaking the carbon-oxygen bond and bringing the electrons to oxygen. This step is forming a water molecule and a carbocation. To get to the final product, I need to do a proton transfer to deprotonate a position beta to the carbocation. I could use water as a base, break the carbon-hydrogen bond, and use those electrons to form the pi bond, and this step would generate the alkene product. So for a secondary or a tertiary alcohol, after the initial proton transfer to make the good leaving group, you have more of an E1 mechanism, with a loss of leaving group before a proton transfer to generate the alkene. A similar type of strategy for activating alcohols to give them a better leaving group is using Lewis acids to coordinate to the oxygen of the alcohol, making it a better leaving group. One method that falls under this category is a substitution reaction involving an alcohol, but instead of HBr, using HCl. Because chloride isn't as good of a nucleophile as bromide, a zinc catalyst is needed, zinc chloride. Our reagents here are our alcohol starting material, HCl and ZnCl2 in the same step, and this converts the alcohol into an alkyl chloride with water as a byproduct. Zinc chloride is an electrophile, and in the first step, oxygen can use a lone pair to donate some electron density to zinc. This forms a new oxygen-zinc bond. Oxygen now has 3 bonds and a positive charge. And this group containing the oxygen, hydrogen, and the ZnCl2 is a good leaving group. In a second step of the mechanism, chloride is going to act as the nucleophile to displace this good leaving group. I would bring in the chloride to the electrophilic carbon and kick out the leaving group in the same step. This forms the alkyl chloride product. Another way of making an alcohol more reactive is by doing a substitution reaction involving phosphorus tribromide, PBr3. This substitution reaction replaces the OH group with a bromine, and it involves an inversion of configuration. So since I started out with a wedge OH group in this case, the dash bromine product is formed. I won't go over the mechanism for this reaction, but if you're interested, you can see it in the textbook. Another type of substitution reaction that you'll see involves SOCl2 and pyridine, a base. These react with an alcohol in the same step. And here as well, I won't show the mechanism, but this has the effect of giving a substitution reaction to replace the OH group with a chlorine, and it'll occur with an inversion of configuration. So here as well, I had a wedge OH group, it's being replaced with a dashed chlorine. This also involves a pretty complicated mechanism, so I want you to recognize the reagents, or be able to predict the product, or use this reaction in synthesis, but I won't ask you about the mechanism. I want to end by talking about alcohol oxidation reactions. So we previously talked about ways to convert a carbon-oxygen double bond into an alcohol by reduction reactions. These were by hydrogenation or NABH4 or LiAlH4 reactions. And this is a reduction, and it amounts to adding hydrogens to a molecule. The reverse reaction, going from a molecule with one bond between carbon and an OH group to a molecule with multiple carbon-oxygen bonds, is an oxidation reaction instead. Depending on the type of alcohol we have present, we can have different oxidations possible. Primary alcohols have the most possibilities. These can be oxidized either once or twice. Here's an example of a primary alcohol where notice the alpha position has 2 hydrogens present on it. I'm imagining treating it with an oxidant, which I'm shorthanding as an O in brackets, and an oxidation reaction could convert this primary alcohol into an aldehyde. Aldehydes, which still contain a carbon-hydrogen bond at the carbon attached to oxygen, are susceptible to further oxidation. So aldehydes can be oxidized to form carboxylic acids, where even more bonds to oxygen have been added in this molecule. Secondary alcohols can only be oxidized once. The secondary alcohol has just one hydrogen present at the alpha position. The oxidation reaction would remove this hydrogen and the hydrogen attached to oxygen to form a carbon-oxygen double bond. For a secondary alcohol, 2 carbon groups are attached to the central carbon for a ketone product. Ketones do not have any hydrogens left on the carbon attached to oxygen, and they are not susceptible to further oxidation. So treatment with even more oxidant would not give you any reaction beyond the ketone product. And last, tertiary alcohols, where you have 3 carbon groups on the alpha position, cannot be oxidized at all. So treatment of these with an oxidant would yield no reaction. For primary alcohols especially, the strength of the oxidant is going to dictate whether you form an aldehyde product or a carboxylic acid product. A strong oxidant would convert a primary alcohol all the way into a carboxylic acid, and it would convert secondary alcohols to ketones. Some examples of strong oxidants that you'll see are chromic acid, H2CrO4, or 2 different chromium reagents, CrO3 with H3O+ and acetone, or Na2Cr2O7, sulfuric acid, and water. Treatment of a primary alcohol with any of these 3 reagents will convert it into a carboxylic acid, where this carbon attached to oxygen in the alcohol becomes this carbon of the carboxylic acid, or treatment of a secondary alcohol with any of our strong oxidants will convert it into a ketone, where it is this carbon attached to oxygen from the starting material that becomes this carbon attached to oxygen twice in the product. I'll term reactants weak oxidizing agents if instead they would convert primary alcohols into aldehydes instead of carboxylic acids, but secondary alcohols will react with weak oxidizing agents to still form ketones. 3 examples of weak oxidizing agents that you'll see are PCC in CH2Cl2 solvent, conditions known as Swern oxidation colloquially, which involve DMSO COCl2 followed by triethylamine, or conditions known as DMP in CH2Cl2 solvent. Treatment of a primary alcohol with any of these 3 weak oxidants, most commonly I will use PCC. This would convert the primary alcohol into an aldehyde, where it is this carbon attached to oxygen that becomes this carbon attached to oxygen in the aldehyde product. To get to the aldehyde product, I removed a hydrogen from oxygen and a hydrogen from that carbon as well. This weak oxidant would stop at the aldehyde product and not go on to form the carboxylic acid by further oxidation. Or if you treated a secondary alcohol with a weak oxidant like PCC, it would convert that secondary alcohol into a ketone instead. Here I've removed a hydrogen from the central carbon and a hydrogen from its neighboring oxygen to form the carbon-oxygen double bond. Alright, so in this video, I talked about alcohol substitution and elimination reactions, and the big idea here was that you had to convert the OH group into a better leaving group to get these reactions to occur. And I ended by talking about oxidizing alcohols. Depending on whether the alcohol is primary or secondary, you can have different products form, and your products also depend on the strength of the oxidant used, especially in the case of primary alcohols. That's it for this video. I'll see you in class.